Going to go through the diesel cycle engine problem. Let's start with simple drawing of our system. So I've got a piston cylinder assembly where my piston can move up and down, and my system is defined as all of the air contained in that volume. And I'm going to use first law Q minus W equals delta E. And delta E can be written as delta U plus delta KE plus delta PE, where I'm assuming negligible changes in kinetic and potential energy. And so finally I have that Q minus W for every process is going to be M delta U. This time the specific internal energy. Okay, so that's one place I could start, and then I'm going to draw my PV diagram for the diesel cycle. The diesel cycle starts with isentropic compression. Start with state 1, so constant entropy process, and then a constant pressure process, then a constant entropy process, and finally a constant volume process. This first process is isentropic compression. The second process is isobaric heat addition. The third process, isentropic expansion. And the last process, isometric heat rejection. So here I've got this last process from state 4 to 1 is my Q out. And this process from 2 to 3 is Q in. There's no heat transfer for processes 1, 2, and 3, 4 because they're isentropic. So I'm going to make a little table of my processes 1 to 2, 2 to 3, 3 to 4, and 4 to 1. And I want to keep track of what the Q is and what the W is for each of those processes. So from 1 to 2, there's no heat transfer. From 2 to 3, there is heat transfer, of course. There's also work because the piston's moving. Process 3 to 4, again, no heat transfer, so 0. Process 4 to 1, there's no work because there's no change in volume. So first I'll establish which ones are 0. Now, in any of the cases where one of them is 0, it means we can use the first law to find the equation for either work or heat transfer. So from the first law, we then realize that work equals negative M delta U. In this case, delta U would be final minus initial, so U2 minus U1. Then for process 2, 3, we have work and heat transfer, so we'll wait on that one. Process 3, 4 is easy. We get minus M, final minus initial, in this case would be U4 minus U3. And then 4, 1 is going to be equal to M, final would be U1 minus U4. Okay, so we have one left, process 2, 3. So what's happening there? We'll need another equation. So we're going to use the equation for boundary work, and that's equal to the integral of P dV. And for this process, the pressure is constant, so it's simply just P times the final minus initial volume. So this would be V3 minus V2. And we could write that as a function of temperatures for an ideal gas. PV equals RT, so we can write R times, actually now I'll need the mass in there as well, so since I'm going to go from PV to MRT, so let's put MR T3 minus T2. Okay, now I'm going to continue to write out my equation for the first law. So I've got Q equals, and it's going to be m delta v. Delta u, sorry about that, times, or plus rather, the equation that I had here. I'm going to leave it for right now as, I'll rewrite this expression as m p and specific volume 3 minus specific volume 2. So I've just divided by m and then multiplied by m. So now I have this equals m u, doing process 2, 3, so u plus p3 v3 minus u2 plus p2 v2. And so I'm just rearranging the terms, and I'm rearranging this because this gives me then h3 minus h2. Our definition of h is u plus pv, and times m. So this is q is m h3 minus h2, and the work is equal to, okay, so to be in keeping with the other terms, I'm going to write this then as h3 minus h2 minus u3 minus u2. Of course, I could write it as just p3 v3 minus p2 v2, but I'll keep everything in terms of u's and h's. So just as a note, this could be mr t3 minus t2 if I wanted to express this entire work terms then. So for that case, I can write it either way. Okay, so let's put this all together. So we've got equations for Q and W, and we've also got all the temperatures now. So now we're going to try and find the efficiency. The efficiency for the for the diesel cycle is still just the net work over the Qn. And if you go back to the table, we had process 1, 2, 2, 3, 3, 4, and 4, 1. And for the first process, we had 0 heat transfer, but we did have work. And for process 2, 3, we had both Q and W. For process 3, 4, we had no heat transfer and work. It was expanding. And process 4, 1, no work, but there was heat transfer. Let me label which ones are in and out. So this is Q in. It was heating in that process, and it was work out. The first process was work into the system. 3, 4 was also work out. So it continued to expand, and then we know we have to have a Q out, but it turns out that process is our Q out. So we can do this a number of different ways. The easiest, since we only have one Q in and one Q out, is to write this as 1 minus Q out over Q in, where we have to be careful that this Q out is the absolute value of Q out, because I've already put the negative in the 1 minus. So when we calculate Q out here, we're going to use the positive value for that. So then I have all my temperatures. So I have T2 equals T1 R to the K minus 1 T3 equals T2, which I'm going to write as T1 r to the k minus 1, so that's T2 times RC, and then T4 equals T3, and we had RC over R to the k minus 1. Now I could simplify that by writing T1 R to the k minus 1 RC times RC over R to the k minus 1. And I'll notice that the r to the k minus 1 and the 1 over r to the k minus 1 cancel, so that one cancels that. And then here I have rc to the 1 and rc to the k minus 1, so I just end up with T1 rc to the k. So that's another way I could write my T4 here. Often we have a pressure ratio given, but for this problem we're using RC. So now I'm going to put all this together into my Q's and my W's. So I've got, well, let me just write out what Q out was. So Q out was equal to M delta U, and I can write delta U as CV delta T, so I'm going to have MCV, and it was T1 minus T4, and my Q in we found out was equal to MCP MCV T3 minus T2. Okay, so I will now write out my efficiency as 1 minus. The sign is going to have to change for my Q out. This is going to give me a negative number, so I'm going to write that as MCV T4 minus T1. And again, the reason for that is I already put the minus sign in 1 minus Q out over Q in. We assumed that all the terms that I calculate are going to be positive, and then divided by MCP T3 minus T2. And we'll notice that the M's cancel, and now I'm going to substitute in my expressions for T4 and T1. So I've got 1 minus T1. Let's actually put the CV in here. So CV times T1 RC to the K minus T1 over CP, and T3 is T1 r to the k minus 1 RC minus T2 is T1 r to the k minus 1. And that looks good. Then I'm going to divide the numerator and the denominator by T1. And let's also divide the numerator and the denominator by CV. So I'll get RC to the K minus 1 in the numerator. And in the denominator, well, the numerator had CV divided by CV also, so that canceled. And then in the denominator, CP over CV, so that was going to be K. and then I divide everything else by 1, or T1, so I have R to the K minus 1, RC minus R to the K minus 1. And now if I go up to the top, where I have my efficiency written as 1 minus Q out over Q in, I can now factor out of the denominator R to the K minus 1, and I end up with 1 minus 1 over R to the K minus 1, which so far is the efficiency for the Otto cycle. And then in the numerator I have RC to the K minus, careful how I write that, minus 1 divided by K times RC minus 1. So I've derived the efficiency for the diesel cycle, and this is for cold air standard. And I notice that I cut off the expression for T4. And I can plug in my values, get the efficiency, and if I want to get all the Q's in the works from the temperatures. I hope that's helped to you.